All right, this is the last lesson. It's just more related rates problems, but they're going to be tougher. We're going to really have to understand what's fixed and what's not fixed. We're going to really want to use the fact that fixed quantities can be plugged into our original formula. We will see that the formula we will be using will not be given to us, and a lot of the times it's going to be a Pythagorean theorem. D squared would be like the hypotenuse of your right triangle. X would be the horizontal distance. Y would be the vertical distance. Okay? If things are fixed, you could plug it into your original equation. Okay? We're going to just get to one problem on this first page and then focus most of our time on the second page. So we'll start with the second one. We did something like the first one, the cylindrical tank, when we practiced today. It was on your quiz. We did something like the pile of sand, practicing as well, and on your homework. So let's just make sure we can do the second one. We have a growing rectangle that has a length that is twice its width. How fast is the perimeter growing if the width is growing at 5 meters per second? We got to know what the perimeter of a rectangle is. That's not going to be given to you. I like to use 2L plus 2W. All right. Now, we are told that the length is twice its width. Length is twice the width. For this rectangle, this is a fixed relationship. Okay. We're asked how fast the perimeter is growing, so that's dp dt, when the width is growing at 5. dwdt equals 5. Since this is fixed, yes, the perimeter of just a random rectangle is twice the length plus twice the width, but the perimeter of this specific rectangle can be expressed by 2 times 2w plus 2w, and that can be simplified. Yikes, my w's and my 2's. I'm trying to 2w plus 2w. 4w plus 2w, it's 6w. Well, now I can easily take the derivative of this simplified formula for the perimeter of my specific rectangle. Derivative of p is dp dt. Oh my goodness. Derivative of 6w is 6 dw dt. Plug in dw dt, which is 5, and I get 30. Talking about a perimeter, is that units to the first power, second power, third power? First power, it's a length, so centimeters per second. Okay? Piece of cake, that's easy. Let's go on to ones that are going to be a little bit more difficult. Skip this pile of sand. We already did that. Let's talk about this situation. Now, pretty much all 3 of these will use the Pythagorean theorem. I like to say it's d squared equals x squared plus y squared. It will be helpful if you draw a picture. For all the other ones that we've done, it wasn't necessary to draw a picture because it was just like, well, I can just take the derivative and I can plug in information. But for these, it will be helpful to draw a picture. And then, of course, make sure you label your fixed quantities. Okay? So here we go. We got a person watching the space shuttle launch. The person is 3,000 feet from the launch pad. just going to go ahead and say there's a 3,000 feet. Okay. How fast is the distance between the person and the shuttle? So here is the space shuttle being launched, and this would be the distance. And I'm trying to find dt. How fast is the distance changing? dt. Okay. That distance is a diagonal distance. So how fast is this distance changing when the shuttle is 4,000 feet high? So I'm going to put 4,000 feet as this kind of height, and rising at a rate of 800 feet per second. Okay. This is where we have x's and y's coming along. X would be a horizontal, y would be a vertical. So rising would be dy dt. Okay. All right. Well, what's going to tie it together to find d dt is the Pythagorean theorem. Okay. However, before I just start taking derivatives, start plugging in information, there is a fixed value that I can plug into that d squared equals x squared plus y squared, where it's, hey, yes, this is the Pythagorean theorem. This works for all right triangles, but for this specific triangle, this will always be the case. What will always be the case for this specific triangle? Good. The x is 3,000. So for my specific situation with the shuttle and the dude, I can plug in 3,000 for x. So I made sure that I labeled this 3,000 as a fixed value. It's always going to be true. The height is not always true, right? Because the shuttle's going up in the air. Okay, well, I can take the derivative now. Now, I don't want to solve for d, take the square root of both sides because that derivative will be complicated. I'm going to keep it as d squared. And I am going to take the derivative of that d squared. Now, the derivative of d squared would be 2d dt. A lot of d's, but one's capital, one's not. One's not really a d. It's like a change. Now, what's the derivative of 3,000 squared? Would it be 6,000? 0. This is very, very important. This is why we did this. When I plugged in a fixed value, you take the derivative of it. This is just the derivative of a number. That derivative is 0. That's awesome. So I don't have to worry about x or dx dt. I just have to worry about y and dy dt. Okay? Now I'm finding d dt. So I have d dt and d here. I have y. Well, the specific moment is when y is 4,000. And dy dt, I was told, is 800. So here's 4,000. Here's 800. But I have a d still. And just like my quiz last class, I want an answer in terms of a number. So there's this extra step that I have to do. What would be the extra step? Perfect. Find what d is at the specific moment when x is 3,000 and y is 4,000. So go ahead and write, hey, I got an extra step. We're going to find what d is when x is 3,000 and y is 4,000. Okay? This is another reason why these are a little bit more difficult. So I get x squared plus y squared is equal to d squared. 3,000 squared plus 4,000 squared turns out equals 5,000 squared. It's a 3, 4, 5 right triangle. Sometimes with these problems, they give you easy enough ones where you can just kind of figure out without having to do many calculations. So now that I got that D is 5,000, I can plug that in there, and then boom, I have everything that I need to find dt. 640 feet per second, since it's units to the first power. Okay, picture helps. What's fixed helps. Doing that extra step, finish things off. Okay, let's go ahead and tackle this next problem. And I want you guys to take more of the lead for this one. We got a 10-foot ladder standing against a vertical wall. So the ladder is just kind of leaning up against the wall like this, okay, on the ladder. Now, the lower end, so my feet are being pulled away, and my hands are dropping down. This ladder is being pulled away, and it's coming down like this. The question is, if it's being pulled away at a rate of 2 feet per second, how fast is the top of the ladder coming down the wall when the top of the ladder is 6 feet above the ground? Go. Start with a picture. Label some stuff. What are you trying to find? What is given to you? What is changing? What is fixed? We understand that this is another right triangle situation, so we will be using d squared equals x squared plus y squared. Can that be simplified? No. I think that's right. Anybody else get negative 64 thirds? Why did you have 64 there? Should be 8. I think you just squared it. Perfect. So it would be negative 8 thirds. Negative 8 thirds. Let's see if we can get it. You don't know that. No. You just know that the x one is going to be 2. Probably should be negative 2. Since it's being pulled away. But we'll find out. As long as we understand what the top of the ladder is doing, the top of the ladder should be moving down. So our dy dt really should end up being negative, or at least we understand the answer and say that it's going down at this rate, then we should be good. Number one important thing, once you understand the situation and what it looks like, is to understand that the ladder is not going to change. The length of the ladder will always be 10. So I plug in and I get 100 equals x squared plus y squared. Nothing else is fixed, so I'm ready to just take the derivative of this. Now, again, the derivative of 100 is just 0, or if you had it as 10 squared. The derivative of x squared would be 2x dx dt. The derivative of y squared would be 2y dy dt. Now, the question is, how fast is the top ladder coming down? We should have written dy dt is equal to what? Okay, so that's the question. So I'm finding dy dt. I plug in dx dt. Now let's say I put it as -2 because I'm pulling it to the left. Let's see what happens. I know that y is 6. I'm trying to find dy dt. And we have this extra step. I need to find x. Well, find x using d squared equals x squared plus y squared when y is 6 and d is 10. So 10 squared equals x squared plus 6 squared. We get that x is equal to 8. So I get 0 plus 2 times 8 times -2 plus 12. This ends up being -32. So I add it to both sides, I get positive 32. I divide by 12, and that's dy dt. That can simplify into 8/3. Now, question.
So since x is growing, why wouldn't it be constant dx over dt?
Right. That's pretty much what we were going to talk about next. If I got an answer that was positive for dy dt, I think about it, I'm like, well, a positive change in my y would be y going up, right? So, yes, we are moving to the left, but like Ms. Watt said, it's not that we're moving to the left, but our x kind of distance here is growing. So it probably would make more sense if this was positive, making this positive, and then this negative, and then we're good, right? That makes sense. However, really, no matter how we do it, as long as we can think about the situation and understand that this is going to be moving down, we could say the rate at which the ladder is moving is downwards at a rate of 8/3. You don't have to include the negative if your answer in your answer, as long as you're saying, it's going down. Does that make sense? Or you can say the rate is -8/3, whatever. We cool with that? Okay, good. Let's move on to this one. So I'm going to draw the picture. We got a fisherman sitting on a dock. Whose reel is 6 feet off the water. And he's reeling in a fish that is skimming at the top of the water. At a rate of 1 foot per second. How fast is the fish moving along the water? Wait. Oh, he's reeling in. He's reeling in. So the reel is moving in at 1 foot per second. The question is, how quickly is this fish moving along the top of the water when the fish is 6 feet away from the dock? Okay, so I'm just writing down the numbers and drawing the picture. You label those correctly and find the correct thing that we're looking for. Okay? It's important that he's reeling in at a rate. So that line, the fishing line, that's decreasing at 1 foot per second. Notice we have another right triangle, so we know we're going to use d squared equals x squared plus y squared. Mm-hmm. 1/3 pi r squared each. Yes.
So like, why would the one be negative?
Well, this is a distance. So this is a distance. This is 1.
Okay.
I mean, this is just 6, right? But we're reeling in. So this line is shrinking in its length.
So it's like a rate of change that's negative, not.
Right. That's why this is dt, not d. Okay? And this is just x. The y is fixed. I go d squared equals x squared plus 6 squared. I take the derivative 2d dt equals 2x dx dt. Then I plug in -1 for dt. I plug in 6 for x. I need to find dx dt. I have to do that extra step. I have to find d. D ends up being 6 root 2 if you know your 45, 45, 90 triangles. Root 2 over 2, root 2 over 2, 1. You just multiply the length by root 2, and you get 1. You multiply this length by root 2, and you get your hypotenuse. Then solving for dx dt, you end up with a negative value, which means the fish is getting closer to you. And that's the rate at which it's moving along the top of the water. Okay? Good. Moving on. We can do the same types of problems, only be talking about the angles and how they are changing. Go ahead and recreate the picture of this guy watching the shuttle. And I'm just going to copy and paste, because I can do that. Guess who's going to help you for these problems? Good old Chief SOHCAHTOA. Okay? Person's 3,000 feet from the launch pad. How fast is the angle of elevation changing between the two when the shuttle is 4,000 feet high and rising at a rate of 800 feet per second? Angle of elevation is the angle between the ground and the sight line of the person to the space shuttle. That'd be the angle of elevation from the ground up. So this theta is what we are looking at. Now the question is, how fast is that changing? We want to find d theta dt. Now, here's the trick for these angle problems, is we're going to pick a trig function, sine, cosine, or tangent. Some of them, pretty much all of them can work, but there's usually only one of them that really you want to use because it's going to make your life easier, okay? And it's based off of the side lengths that you're given. So I'm given this side length, the x length. This is the fixed length. We need to understand that. And I'm given the y side length. That's the opposite. This is the adjacent in reference to this angle. What trig function do you think we should use? Right, tangent, simple, opposite, adjacent. Now, I don't like to use opposite and adjacent. I like to stick with x's and y's. But we will start with just tangent of theta is equal to opposite over adjacent, y over x. Well, if I took the derivative of that just right away, I'd have to use the quotient rule for the derivative of y over x. I don't want to do that. What can I do? Perfect. I have a fixed value. So yes, for a given right triangle, this is true. But for this specific right triangle, in this specific situation, the x value will always be 3,000. And you know what? I'm not even going to write it as y over 3,000. I'm going to write it as 1 over 3,000 times y. That way, I don't think of crazy things when I'm taking a derivative. And that's what I'm going to do next. I'm going to take the derivative of both sides. Oh man, what's the derivative of tangent? Secant squared. Some of us remembered that. I'm sure not all of us. That's okay. Now this is great. The right side is just 1 over 3,000 dy dt. Okay? Well, I can plug in dy dt. It's 800. And I'm trying to find d theta dt, but I got a problem. I got that I need to figure out. Here comes my extra step. Now, it's important to understand that secant squared of theta is the same as the secant of theta squared. Right? Right. Well, actually, since I know a bunch of my side lengths, and really, if you remember back, we know that d at the moment when x is 3,000 and y is 4,000 is 5,000. Remember that. We can use my side lengths to find the secant of the angle. It's just going to be equal to a ratio. Now, what ratio is it equal to? Well, it's the reciprocal of cosine. Cosine of an angle is equal to my adjacent, or my x over my hypotenuse, which is d. That means secant of my angle will equal d over x. Well, in this case, d over x is 5,000 over 3,000, or 5 over 3. I can take what secant of theta is equal to and plug it in and square it. And I get 25/9. That's a piece of cake. And then all of a sudden, instead of worrying about secant squared theta, I just worry about 25/9, and I solve for d theta dt. 8/30 times 9 divided by 25. I'm going to get some decimal. What do I get? Really? What is it? .096? That sounds about right. Yep. I get 12 1/25. Check your work. Now, this is a change in an angle. We do these in radians per whatever time measurement. Okay? Again, see how this is a little bit more intense than last week's problems. Okay? Now, we're going to skip this one with the ladder, and we're going to go back to the fisherman. I'll show you the one with the ladder on the website, on the video, if you want to see it. So let's go ahead and recreate our fisherman picture. Everything is the same, but we need to find how quickly the angle between the water and the fishing line is changing. Okay? Well, what should I be using? Sine, cosine, or tangents? Should I use tangents? Because I got that 6 and that 6. I would recommend not using tangents. Unless you went and already did the problem that we did before and you already found dx dt. But if I was doing this problem from scratch, I'm going to use the fact that I know what d dt is. And I know that this is fixed to use sine. Because I know what d dt is. Okay. And again, we can plug in our fixed values. Well, we talked about how the fisherman's pole's height is fixed. So I can write sine of theta is equal to 6/d. Now, the reason why I skipped the previous one and went to this one is for this situation. Taking the derivative of sine of theta, which equals 6/d. The derivative of this is not 6 times d dt. It's wrong. The derivative of this on the right side is not 6/d dt. Why not? Because this is 6d to the negative first. Okay? So I would rewrite, if I have something in a denominator, as 6d to the negative first. And when I take the derivative of the left side is cosine. That's easy. The derivative of the right side is negative 6d to the negative second, which is negative 6/d squared, dd dt. Now, we remember that d in this specific instance was 6√2. That's changing. So I can plug in 6√2 and square it. That would be 36 times 2, which is 72. And I know d dt is -1. I'm trying to find d theta dt, but I need that extra step, cosine of theta. What's cosine of theta? Well, cosine of theta is equal to the ratio of your adjacent side over the hypotenuse. The adjacent side is 6. The hypotenuse is 6 root 2. This is just 1 over root 2. Now we're ready to go. This is 1 over root 2. D theta dt is equal to -6 over 72. Can that be simplified? That's 12. Positive 1/12. So that ends up being root 2 over 12. Rads per second. Okay, so angles, tougher. There are two more that are even tougher than that. Deals with, well, some people think the angles are the toughest. Deals with fixed proportions that you must create. I'm going to walk you through this problem pretty quickly because I want to get through the next two and show you before you guys take off, okay? So, just stay with me. We got water draining from a conical tank. Now, a conical tank is going to be vertex down, looking like this. This is our tank. Okay? We got water in this tank, and we're going to be talking about the volume of this water. Now, the radius of the tank is 10. The height of the tank is 25. The water's draining at 3 cubic inches per second, so that would be dV dt.
So how do you know it's the other way? Like, doesn't that matter?
It does matter a bunch. You will be told it's vertex down.
Okay.
And when we talk about conical tanks, if you think about it draining from a tank, yeah, maybe you have like a hole in the middle if it's the other way around. It could be, exactly. But then like maybe water would get stuck kind of on the outside there, you know. You don't want that to happen. So think about like one of those little cups that you get at golf courses. That's our conical tank, okay? You guys know about those, right? Okay, great. So question is, what is the rate that the radius is changing? Okay, now you'll be told that the volume of a cone is 1/3 pi r squared h. Great. What is the rate of the radius, and we're talking about the radius of the water changing when the height of the water is 15. So we're told that the height of the water is 15. And if this is r, we're going to find dr dt. Well, here's the problem. As the water is getting drained out of my tank, both the r and the h are changing. So yeah, I say this is 15, but I want to give that a variable h. And we're looking at dr dt at the moment when h is 15. Well, I don't want to take the derivative of this because this is nasty and I'd have to use the product rule. So I want to try to simplify things. I want to make this a specific formula for this specific cone. And what's going to help me simplify things is the fact that we create two similar right triangles, which is the radius and the height of the tank and the radius and the height of the water. Okay, these triangles will share two angles. That means the ratio of their sides will be proportional, which means the ratio of the radius of the water to the height of the water will equal the ratio of the radius of the tank to the height of the tank. Now, I'm trying to find dr dt. This is what we will call our fixed relationship. It's not just a value. It's like that whole sand pile. Height 3 times the size of your diameter or something like that. You know, we aren't told that. We have to create that. Okay, now I want dr dt, which means I need r's here. So I want to get rid of h and replace with r's. Which means I'm going to solve for h down here. H will equal 25 over 10r, or 5 over 2r. I take that and plug that in for h. And now I have a specific formula for the volume of this water in this tank, not just the volume of a random cone randomly. I can simplify this. This is 5/6 pi r cubed. We are now ready to take the derivative with respect to t. I get dv dt is equal to 15/6 pi r squared dr dt. I know dv dt is -3. Well, there's one more thing I have to find, is h, r, when h is 15. So I'm going to actually go back here, and this is going to be my extra step to find this r value. I'm going to plug in 15 here. 15 times 10 divided by 25. I get 6, which is nice. And I get 15 over 6 pi 6 squared dr dt. And I solve for dr dt. Okay, so -3 times 6 divided by 15 pi. So that's 18 over 15 pi, which is -6 over 5 pi. Okay? Rewatch this if you don't understand it. Okay? It's all about this proportion that you come up with. Moving to the last problem. Again, this is another difficult problem. Okay, so we got a lamp post with a height of 20 feet. Here's my lamp post. It's 20 feet high. It's shining on a 5-foot tall person who is 10 feet away. And it's creating a shadow. Okay, so the light's coming off here, hitting this guy, and creating a shadow. How fast is the shadow increasing? So I want to find ds dt if I'm using s for the shadow. The person's walking away, so that'd be like dx dt at 2 feet per second. Now what's first really important, that the only thing that is fixed is this 20 and this 5. This 10 is not fixed, so I'm going to replace it with a variable like x if dx dt is 2. Now you'd think you would need the Pythagorean theorem, but actually your formula comes from the proportion. And the proportion is from two similar triangles. We have this outside triangle here, and then the triangle that is just created right here. So if we think about the two lengths that will be proportional, it'd be the height of the lamppost and the distance to the tip of the shadow, which we'll write as x plus s. That will be proportional to the height of the dude to his length of a shadow. This is it. This is the formula you need. You can then cross multiply and simplify this formula, and you'll notice that this ends up being very simple to tackle. This is 15s is equal to 5x. You take the derivative with respect to t. You get 15 ds dt equals 5 dx dt. You know dx dt is 2. So ds dt is 10 over 15, which is 2/3. That would be a unit to the first power per second. Okay, so that one's tricky if you're not familiar with it. Let's go back and do the last example, which is our ladder and our angle of the ladder. So again, let's grab the ladder situation that we drew up. So the upper end of the ladder is being pulled up, so some stuff has changed. We were told the upper end of this is being pulled up, so that's dy dt is 2. Question is, how fast is the angle between the floor and the ladder, that'd be this angle here, changing when the top of the ladder is 6 feet above the ground? So again, I see that I have an opposite length. I have dy dt, and I have an hypotenuse. I'm going to use sine again. I'm trying to find d theta dt. So sine is going to be equal to my opposite over my hypotenuse, but I'm going to simplify it since I know that the hypotenuse is always 10. I will rewrite that as y times 1/10. Then I'm ready to take the derivative of it. Derivative of sine is cosine theta d theta dt. Derivative of y dy dt times 1/10. And now I know what dy dt, it's 2. It'll be 1/5. Trying to find d theta dt. I just need to find out what cosine of theta is. So again, here's my extra step. Cosine of theta will be equal to an adjacent side over a hypotenuse. I know the hypotenuse is 10. I need to find x, like extra 2 steps. So here x squared plus 6 squared will equal 10. I end up with x is equal to 8. It's a 6, 8, 10 triangle. So now I get cosine of theta is equal to 8 over 10. So this can be replaced with 8 over 10, and I could solve for d theta dt. Multiply by 10 divided by 8, I end up with just 1/4. This would be rads per second. I'm going to think about this problem. dy dt is moving up. Is this angle going to increase? Yes, the angle is going to increase, so the sine looks good here. Okay, that's it. Those are our tougher related rates problems that we need to be prepared for. Thank you.